to absorb all this information straight away. So go rewatch our YouTube channel. It's Daikin South Africa, and go on the YouTube channel. You'll see this video linked. Also, please subscribe to the Daikin South Africa YouTube channel, and if you click like and that on our videos, you will get subscriptions or all our latest trainings, technical trainings, as well as technician trainings to help the guys with any problem finding techniques that they're having. Just got to find out where my share screen is, sorry. Okay, just a heads up, you can see my full screen, please, and you can hear me? Anybody?
Yes.
Okay, thank you. So please, just throughout the training, remember to mute your microphones. I cannot see if you push your video screen on because I'm in presenter mode, but please make sure your cameras are off because other people will be able to see you. I cannot see you, so please make sure your camera's off. Okay, so today's training will be on voltage imbalance and how it affects electronic circuitry. The main thing with this kind of training is a lot of people think over voltage. Sorry, somebody's microphone's on. Please, everybody mute your microphones for me, please. Thank you. Sorry, I'm going to have to mute because the person's not muting the microphone. Give me a second. It's George not muting his microphone. Thank you. Okay. It's muted. I've sorted the problem out. Thank you. Please make sure your microphones are muted. Right, thank you. So as I said, a lot of the problems we have on electronic circuitry is not primarily due to over voltage. It's mainly due to under voltage. So I'm going to go through this training. It'll be about an hour long. And hopefully you walk away with some very valuable knowledge. So I think before we start this thing, we're dealing with voltage. It's very important to understand the difference. Just a little refresher. Some of you might not know this, others might know it, but the difference between alternating current and direct current. So our power generator, our utility provider, or even a generator that you're running at home will supply you all your power in an alternating waveform. That is why we call it alternating current. AC is obviously stands for alternating current, and it's primarily voltage oscillations between a positive and a negative cycle. So we call this oscillations frequency. So there we have a positive and a negative, and as the turbine is spinning, it's producing through electromagnetic inductions, peak voltage is there, zero voltage, peak voltage, zero. And that is what we pretty much get supplied along our power lines to operate our premises. The next thing we deal with is direct current. So if you see with DC voltage, it's a straight line. So there's no voltage oscillations. So therefore, DC also doesn't have a frequency. In South Africa, we oscillate at 50 hertz. So technically this wave switches on and off 100 times a second, and it switches in 200 milliseconds. So if when you get shocked by something, you're getting you're getting a peak voltage shocking you 100 times a second. It shocks you, then releases you, then it shocks you, it releases you. And these pulses, this wave train, it triggers in 200 milliseconds. So we see the dotted line at the top. If we translate that right across onto the DC graph, we call this peak voltage, and you'll notice there's no peak voltage with DC. But we do have what we call an effective RMS voltage, which runs across here. So this is an important little word to remember. It'll come up later on in the training. But primarily, with electrical supplies, your meter, when you measure your home appliances, for example, single phase, you'll get, say, 220 volts. It's actually not measuring the peak voltage, it's measuring this voltage. So if I take this voltage across, it's root mean squared. It's a power voltage calculation, and this is the same sort of power that a DC source would give you. However, you are getting a lot more than 220 volts out of your wall plug. Okay, you're going to be getting in the region of about 320 volts coming out of the plug. So that's an important thing to remember. As I said, as we go through the training, I'll explain that to you. So the frequency, therefore, of alternating current is determined also. Remember, frequency is how often something switches on and off, how often something flows. That's called the frequency. So that is, how is that determined? It's determined by the rotational speed of the magnetic field cutting the stator coil. So in a nutshell, it's telling you how fast the mechanical shaft is spinning at the power station that's connected to a steam turbine. And it's normally for AC about 3,000 revolutions a minute. That's how fast it's turning. So now that we know the basics of AC and DC, the difference between them, alternating current shocks you, releases you, shocks you, releases you. Direct current does not release you when you touch it. It doesn't oscillate. So it's a lot more dangerous. AC is more dangerous because it's got higher voltage, but DC is more dangerous because it has constant power. It doesn't release you. So a very important thing to understand in circuitry when you open up an air conditioning unit and you see where the electricity goes in. Downstream, you have what you call a diode. And that's pretty much what a diode looks like. So what is a diode? A diode is an electrical device that's made out of silicone that allows allows the electric field or current to only flow in one direction. In order for a diode to conduct, it requires electrical pressure, which we call voltage, okay, of 0.06 volts. And it possesses extremely high reverse bias voltage characteristics. I'll explain what all this jargon means soon. But it is due to this high reverse biasing that a diode prevents the reverse current flowing back into an electrical supply. So when a diode is forward biased, it behaves like a short circuit and it will conduct. And then when it's reverse biased, it acts like an open circuit, like an insulator. I'll get to the little farm gate story soon, but an open circuit is like when you flick your switch in your bedroom, your lights go on. When you flick it the other way, it switches off. When they're off, it's an open circuit. When you flick the switch down, it's a closed circuit. When you flick the switch down to put the electricity on, it requires pressure from your finger. It's not going to do it by itself. So that pressure that we would have here requires 0.6 volts of pressure. So that is the voltage drop I'm going to get. So if I put 10 volts through a diode, 0.6 volts of that pressure is going to be used to make it switch, and I'm only going to have 9.4 volts coming out of the diode. So we do have a voltage drop. The reason I put a farm gate here, for an example, is that a farm gate, imagine you get out your car and you push open a farm gate. It also requires pressure. The farm gate will open one way, and then if you try and push the farm gate the other way, most times there's a pole in the way. And you can push as hard as you want on that farm gate. It's not going to move. It requires incredible power to break the pole at the ground and let the farm gate open the other way. This is the secret about a diode. It's like somebody's trying to push the farm gate back against a wooden pole in the ground. It's not going to go anywhere. It requires incredible amount of strength. Even if you do have that strength, you're going to eventually break the pole at the ground. The farm gate's going to swing open and it's going to break because it's going in the opposite direction per se. And in the same way, your diode will explode if your breakdown voltage is exceeded. So a diode conducts current from an AC line in what we call a discontinuous manner due to the fact that they only conduct on the peak of the AC waveform. And this then creates nonlinear waveforms. So these are big words we're using, but they're the correct engineering words that we have to use. So remember what an AC waveform looks like. Here it comes into the diode. Okay. Now it will take 0.6 volts to push this waveform through the diode. But now it pushes through. And here it peaks through. Now this is the farm gate scenario. It can't go backwards because there's the post. So it doesn't conduct here. So all the red waveforms do not conduct. They're getting pushed back by this device's post, if you want to call it that. Then it will come in here, it will conduct. It will only conduct when it reaches the peak waveform. And remember, I showed you the peak waveform. In AC, it's around 320 volts. How do we get to 320 volts? You take 220 volts and you multiply it by the square root of 2, which is about 1.414. So you take 220 times it by 1.414, you're going to get your peak voltage. So when we have the peak voltage, the diode is going to allow it through. When it drops below here, the negative AC cycle, it won't conduct, so it's just 0 voltage. Then it'll, over here, it'll start reconducting, and it will allow this camel hump, and it won't conduct. So that is the principal operation of a basic diode. And this, because it's only one diode, we call it half-wave rectification, because we're only rectifying the half of the wave. We're not rectifying the bottom half of the wave. So why do we need to rectify? Why do we need to modify this waveform that the power station is giving us? Well, let's have a look. Here's a typical bedside lamp that you have next to your bed, your AC source coming in from your plug. And we'll have a look on the top half. When it goes through your diode, my lamp will switch on. And the voltage isn't going to go back to the plug, it's being blocked. So if I slow this down as a figure of over a function of time, we will see that the light bulb, instead of switching on and off 100 times a second, now it's only going to switch off 50 times a second. This is what we call half-wave rectification. So this kind of rectification is not very popular. In the good old days, they used to use this kind of design as a light dimmer. If you didn't, before you had variac control, you would let your bedside lamp only glow half as bright now, switching on and off 50 times a second. You wanted it brighter, you let it switch on and off 100 times a second as the electromagnetic wave travel through the tungsten filament. So half-wave rectification is common though in what we call switch mode power supplies. And it's responsible for generating what we call even harmonics in power systems. So there's two new terminologies I've introduced you to: switch mode power supplies and harmonics. What's a switch mode power supply? Switch mode power supply is anything that will take an incoming voltage, feed it through a transformer, and give you multiple voltages coming out of the transformer. Prime example is the old computers, the towers. You put your electricity in and you would have a 5-volt rail coming out, a 12-volt rail, maybe a 40-volt rail, a 3-volt rail. Each of those voltages control different parts of your computer. Even the charger that charges your laptop computers nowadays is a form of what we call a switch mode power supply. It's switching a lot of these fancy voltages, going through transformers and switching them at very high frequencies and generating multiple different voltages. Even on our VRV, not our VRV, anything inverter driven on the Daikin equipment also goes through what we call switch mode power supplies. We have different voltages supplying the pressure transducers, the temperature thermistors, the fan motors. All of that need different voltages, all chopped up from one supply voltage of 230 volts. So that's what a switch mode power supply does. And it generates harmonics. We'll get onto harmonics, but a lot of you may have heard there's problems on sites. People say, your inverter technology is creating harmonics on our system and it's blowing boards and all of that. But we'll touch on that just now in the training. So now we look at full wave rectification. What we've been talking about is half wave rectification. So let's have a look at what full wave rectification does. So as we can see, we put our device in the wall, we switch on, put the plug in the wall and we switch it on. And now we will see this AC waveform. it comes down. There's 4 diodes now instead of 1. So that the power supply will come down, it'll go through my load. Let's say this load's a lamp, but you don't need a bridge rectifier for a lamp. But let's say this load could be anything that needs like a DC voltage to operate. It will come through the diode, go through the load, it'll come up. It can't go through this diode because there's another little blue line that would come down here and it would block it. So it can't go there, so it's forced to go through this diode. It also can't go through this diode because it's going to encounter this voltage going through. So the only free path back to the plug and back to the transformer in the road is to follow that diode. So when I go through these 2 diodes now, I get this full wave coming up. Now, as the magnet in the power station now turns from a north-south to a south-north, I get a repulsion of electricity. And now, because I get a repulsion, the electricity goes the other way. But notice it's still going the same way through my load. It's always coming through my load, through the top of my load. So even though the magnets are back to front, they still go through the top of my load. So you see now it won't go through this top diode and the bottom one, but it'll go through the bottom, this lower diode, through my load, up and back to the transformer in the road. And now you'll notice, interestingly enough, I have this red pulse coming through, which I didn't have on the other diode. On the single diode, I had a red line here, but now somehow I have this also coming through, and it's not below the line anymore. It's now somehow flipped and inverted, and it's facing the top of the line. So notice that although the input supply is oscillating, the output current is always positive. This is what I've alluded to. It's positive. It's above the x-axis. So what does this mean? This now ultimately means we have positive power. Diodes are used on a bridge where the input current is around 50 amps or less. Silicone control rectifiers, or SCRs, now are used for 50 amps and higher rectification. Input frequency is not affected by the bridge because diodes only conduct when they forward bias. So that's a big fancy word, but on smaller, anything 50 amps of power coming in or less will use these kind of diodes. So this is pretty much what a bridge rectifier looks like. When you open an air conditioning unit and you see all the electronics, you'll more than likely see this unit. When you got into our bigger systems that draw a lot more power, you'll see bigger versions of this, and they'll have big heat sinks bolted onto them. This will just be cooled by air. They're very rarely bolted to big blocks of aluminium because they're not drawing as much power. When we start going to 50 amps or more, we'll start using these, and then we'll use SCRs which look different to these. But for the purposes of this exercise and the training I'm doing, this is all I want you to visualize for now. This is what a bridge rectifier looks like. So let's see single phase, full wave rectification in action. So here's, I put my plug in, and we've seen what the bridge rectifier does, but importantly, we now have all that red or negative pulse has been flipped upside down, and it is now positive. So importantly to see, the output now is a DC wave, but it's far too unstable to use. Now notice, even though this has got humps, it's not alternating. It's still direct current. If it was alternating, it would alternate above and below the x-axis, but it's not alternating, so it's always above the x-axis, so it's direct. There's no alternating involved, so it's always direct current. Okay, so don't be fooled because it's got humps that it's not DC. Unless it drops below the zero potential or x-axis, now this becomes alternating. This is all DC because it's always above the x-axis. But this is too unstable for us to use. I cannot use camel humps of power like this. So it's actually oscillating also at double the supply frequency. So this is actually switching on and off now at 100 times a second, okay? And in this case, it's oscillating, it's actually switching off 200 times a second because it's now oscillating at 100 hertz. So a supply of this nature wouldn't be of any use for powering circuits, because any analog circuits would have huge levels of what we call voltage ripple superimposed on the output. And any digital circuits won't function because the power would be removed every half cycle. We can also see from this voltage train that we'll be delivering very unstable power to the load. I've used the color yellow here to show you that this is constant power. If you remember what DC looks like, nice good DC, it's a straight line. And if it was a nice straight line, all these white areas would also be colored in yellow, and I'd have constant power coming through. So here we see this is a direct current output at 100 Hertz line frequency. So I've doubled the supply frequency just by flipping the negative half cycle on above the x-axis. And here we can see this is very unstable power. We cannot use that. So now I put you at the bottom. This is where capacitance comes in. What is a capacitor? We often see them, we hear them. What do they actually do? Okay. So a capacitor actually stores energy. So what is energy? Energy is the ability of a system to do work. Okay. So a capacitor stores energy and it supplies power to the load. So power is how quickly work is performed. So if you hear the word 200 kilowatts, it can provide 200 kilowatts of work in 1 hour. Okay, that is why Eskom charge you in kilowatt hours. How much power have you used over a function of time? I've used 2 kilowatts or 5 kilowatts in 1 hour. So power is how quickly I'm using the energy. So capacitors will also store a higher voltage than the measured RMS supply voltage on your meter. Remember the first slide I showed you, I said this, you remember the word peak voltage. So this is where the little tricks come in and a little bit more understanding of why capacitors store higher voltage than you measure on your meter. And why do they do this? Well, this is because capacitors charge to maximum value on the peak of the sine wave, namely peak voltage. And I said to you just now, the peak voltage for single phase, I'm going to stick to single phase for now. We all sort of can relate to it in our homes. If you measure a capacitor, let's say you open a circuit at home and you want to be brave and you see the bridge, you'll see your supply capacitor. That's what it looks like. And you put your meter on there. If you put your meter on AC, you're not going to measure anything. Why? Because remember, we're DC now. So you've got to put your meter onto DC. You put your meter onto DC, and you're suddenly going to see that you're getting about 320 volts across these pins. And you say, how's that possible? You put your meter on AC, and you're only getting 220 volts in you. Well, it's simple. It's because the cap will only charge on this peak voltage. It'll charge to maximum on the peak voltage. And remember I said to you, you have what you call an effective RMS voltage, which is just 220 volts, and that would be a line at this lower level. That's what your meter would measure. But in reality, what's happening at the physical level and the fundamental level, your capacitor is charging to 320 volts on these peaks. So this is what an ideal capacitor would look like. So when the capacitor just charges up and it doesn't supply a load, then we have what we call a linear waveform of voltage draw of the bridge rectifier. Now, I'm using big words here. Linear means straight. So this orange line is straight. And secondly, the capacitor is just charged up. It's like a water tank. It's charged up and nobody's opening any taps to shower or flush the toilet. So the water tank stays full. Doesn't need to do any work. It doesn't need to deliver any water for any useful work. I've also said here that the linear waveform of voltage draw from the bridge rectifier. So this capacitor is drawing power out of these diodes when it initially charges up. That's why it's drawing power until it's fully charged, and it's sucked this power out of these diodes, and it's not doing any work at the moment. So what do capacitors do? Capacitors oppose a voltage drop in a circuit. When a voltage drop is detected by the capacitor, namely when the load draws power, then the capacitor reacts to this drop in microseconds and delivers large amounts of the required power almost instantly. When this happens, we drain the capacitor now, okay? So the capacitor is waiting there loaded. It's like a tap. As you open the tap, water is going to flow, but it's going to take the pressure in the water tank to give you instant water. And the same thing, the capacitor has stored energy. So here's the capacitor. Now suddenly a motor starts, or you flick a switch. Primarily anything that has to do with rotation is when we use these switch mode, or this in this case, this capacitor. Because we're talking air conditioning, this would primarily be used to supply power to your compressor to create rotation. So it supplies power to the load, and the capacitor supplies energy as the rectifier voltage falls. So as the capacitor starts supplying power, it drains, and you see this orange line starting to drop. But my transformer in the road quickly supplies me more power, and the capacitor charges up from there. Remember, this is happening about 200 times a second. It's happening very fast. So now the capacitor draws energy from the bridge now on the near peak value. So this bridge, the capacitor, is drawing power out of these diodes. So unfortunately, when the capacitor supplies power to the load, it creates what we call a non-linear voltage draw from the bridge rectifier. Now you notice this line's not straight anymore. It's humped. It's like crinkle cut, okay? Why? This is because the capacitors start to draw energy from the bridge, which is here. Why do they do that? Well, they need to top themselves up back to maximum value again, volume again. It's like your toilet. You flush the toilet, makes a noise. Why? Because it needs to charge up again. And what switches it off? The ball valve in the toilet. This is very similar to flushing a toilet, okay? So the capacitor, it only draws this voltage now on the peaks of the sine wave, which I've told you. And this is this is where the problem comes in. This discontinuous waveform now is called ripple, and is one of the main causes of harmonics in a power system. So I said to you, this is ripple or crinkle cut effect. So capacities draw energy from the peak on the, the capacitors draw energy from the bridge on the near peak value, and this is this little discontinuous non-linear ripple waveform we get into. But I've said we'll get back to this a little later on in the training. So now this is where we separate a bit of the men from the boys when we start going to three-phase rectification. Nearly all the big sites you guys will work on will be non-residential, and they will run primarily in South Africa on 400 volts. A lot of our supply is 400. Certain countries like the UK or whatever might get 380 volts, and certain European countries 415 volts. Now this is quite a much more complicated looking circuit, and you'll notice now we don't have 4 diodes, we've got 6. Three-phase rectification requires a minimum of 2 diodes per phase. One allows the passage of current when the supply voltage is positive, and the other when the voltage is negative relative to the 0 voltage reference of the y-axis. Sounds all complicated, but I'll show you what I mean. So this is the case, thus, in the case of an entry-level 3-phase power inverter, the rectifier will have a minimum of 6 diodes, and we call this 6-pulse inverter technology because we have 6 pulses. There's the 1, 2, 3 phase, and we need 2 diodes per phase. Providing more diodes per phase reduces the number of harmonic distortions within a power network. We'll see a little bit more about this further on in the training. So variable frequency drives are becoming more and more common in industrial and commercial establishments as a means of controlling rotational speed of shafts within motor assemblies in the most efficient manner without sacrificing any performance. It's also very important why we use VFDs is there's no lock rotor amps, and therefore there's not much electromechanical stress on your switch gears. and we don't need a lot of what we call power factor. So there's a lot more gentle approach on the supply transformer supplying the building or the factory. It's also not a well-known or understood fact that voltage imbalance can be detrimental for variable frequency drives on the front end circuitry, namely the rectification from AC to DC. And that's what we've been looking at. We call that the front end. Why is the front end? Well, it receives the voltage first. So it's at the front, it's at the top of the river, it's by the waterfall. Okay, so that's where we get power. It's called the front end, and that's where the primary action takes place. So now let's have a look on how a three-phase bridge rectifier is going to work. You might see a diagram like this at times. It looks very intimidating and very confusing, but I'm going to hopefully deconstruct this a bit for you. And how am I going to deconstruct? Well, I think it's better to get an understanding of current flow by redrawing the circuit. That looks very confusing. And I think it's better if we draw it like this. We've taken those diodes and I've reconstituted them in this way. It's a bit more easier for you to understand. If we look at this basic diagram, you'll see you have your live 1, live 2, live 3, but interestingly, they're all joined with what we call the neutral. This will be joined at the transformer. Nearly every supply transformer that supplies a building or a factory will be star connected, and that neutral wire will be nailed, or not nailed, connected to a big earth spike at the supply transformer. I'm not going to get too much into this training what the neutral does, but I've just drawn it in there for correctness of the drawing. So here we see a far more easier drawing. The power will come in through these diodes, do work through the load, and it's going to leave the load, go back through these diodes, and go back to the transformer where it's been supplied from. So what the heck's going on now? I've added these very confused looking graphs, but don't be intimidated by them. I'm going to hopefully use them to explain to you what's actually going on here. So if I look at the top here, I put 3-phase in here. Now, which diode would the current know to flow through first? If I plug this in, which way does electricity go? Does it go that way? Does it go that way? How does it know which way to flow? It doesn't have a brain. It's just a wire that's carrying, it's a wire which is a waveguide for the electromagnetic field. And the electromagnetic field doesn't know which way to flow. So if we have a look at this 3-phase supply that's coming in, and it looks a lot more confusing than the normal single-phase one I showed you. This is what 3-phase looks like. And 3 phases are separated by 120 degrees, electrical degrees, and you add 3 times 120 equals 360, which is 1 full revolution of the steam turbine. But now let's look at this section on the graph to help us understand the flow of current through the bridge. So I've put this little green block around this very confusing looking bunch of lines. So if we look here, we see that the blue phase is on the positive y-axis and on the increase. If I look in this little window only, I see that the blue phase is on the positive axis, meaning it's above the y value, and it's in the positive of the y value, so it's in the positive value, and it's on the increase. You can see it's busy climbing. The red phase now is dropping in voltage. So here you can see the red phase is dropping. It's going below the 0. Let's say this is, say, 400 volts. It'll be more. It'll be about at a 400 volts peak. We're looking at about 520 volts here. So imagine this is 520 volts, this line, and here's no voltage. So we can see that in this window, the red voltage is busy dropping to 0, and now it's going negative. Negative, by the way, doesn't mean it's not going to shock you. You touch this here, you're still going to get zapped. We just create the negative term for mathematical calculations and better understanding. And then we'll also see here that the green phase is the most negative here, meaning it's minus 520 volts, and also dropping. So it's minus 520 volts, but it's climbing to maybe 200 or 300 volts. So I know this sounds very confusing, hence I'm saying watch the YouTube videos and re-watch them. We are recording this to try and get a good understanding and a grasp of three-wave rectification. So now we see the blue phase. If you look at this pink little line that's flowing here, the blue phase will have the most positive voltage, and it's this phase that will allow current passage to D1. So I'm going to erase it. I'm going to show you again. At this moment in time, remember everything happens in time. This is happening 200 times a second, sorry, 100 times a second per phase. So that's actually 300 times a second. This is happening, and it's happening at 200 milliseconds per phase, very fast. So if we look here now, I'm going to draw your attention to the blue phase. The voltage is coming in, and it's going now, because of this graph, it's going to go through that diode first, through the load, and now it comes to voltage to D6. Now it has to decide which diode to go through. It can't just choose any path to go through, because you're going to have a big explosion on the front end. And I'll redraw this animation, and we're going to come to D6. Now we get here, which path does the current choose to take? The current will want to pass through the diode where there's least voltage. It doesn't want to have to work. It wants to easy passage, okay? So therefore, the most negative, as per Kirchhoff's voltage law. So in this case, it would be the red phase, okay? Which in our which is what we call our phase C on our schematic. So the current will flow through this route. If the other diodes try to conduct, it will be a violation of Kirchhoff's voltage law, which is a mathematical equation. A lot of times we don't understand things, but we use mathematics to prove. And this is the path. So you notice, interestingly, it came in on the blue phase, and it returned to the transformer on the red wire. So yes, three-phase is a very complicated subject. It requires immense timing, actually very accurate timing to know. Timing is critical, because you cannot have one diode switching off. Well, they don't technically switch off. They're passive devices, but you have silicon control rectifiers, which we'll get onto just now, and they conduct on what we call gate voltages. So timing is critical, else you're going to blow up all your electronics. So I'm just going to fast forward through a bit of this now. That was primarily to just show you so what happens in that specific moment on time. So if I took this green block and I slid it further down, I would be moving our circuit analysis as a function of time to see what happens. And then what we would see is, as we moved on as a function of time, now the path wouldn't return through the red wire. It would return to the yellow wire all the way back to the transformer in the road. And all this is happening very, very fast. Now you'll see suddenly that the red wire decides to push through first, and it goes through the bottom diode, and it returns through the yellow wire. And we'll do one more simulation here to show you how variable three-phase rectification is. And now it returns to the transformer through the blue wire. So now that we're all nice and confused about three-phase signals and phase angles, we turn our attention to the middle graph to show what happens to the waveform. Because it's all good and well showing this voltage going through all these things. What does it actually mean? It has to serve a purpose, else it's a pointless exercise. So let's focus on these three diodes. So the top set of diodes will rectify on the positive y-axis. So any action that happens above this line, all these peaks, these three diodes are going to cope with them. And if you notice here, I'm drawing this, I've drawn this wave train, I've highlighted it. And if we now look at the bottom set of diodes, that's the negative rectification, we will see that it no longer crosses the zero potential. It's like we have positive power and negative power, but there's no such thing as negative power. You don't do negative work. So what do? We do a bit of mathematics, and you subtract the values of the two portions from each other on these peak waveforms. So I've added these arrows in. You do a bit of maths, and then what we do is we'll end up with a positive waveform, which is on the top here, and that is my power. So I've rectified the top half, I've rectified the bottom half, and I've flipped through mathematics the purple on top of the green. I've added them all together, and we have a lot finer waveform now. You see these waves here are quite big. Now they are much smaller. And notice that the top red wave train now is also higher on the graph. So look, now I'm getting much more voltage and power out of it as well. And this is because this is a peak line to line voltage and not line to neutral. So a lot of times you guys put your meters on, you'll measure between the red and say the yellow or the red and blue, and you will get 415 volts. When you hold your meter probe on only the red wire and you measure the neutral, you suddenly say, hey, hold on, I've dropped to 220 volts. So that is what they mean, line to line voltage and not line to neutral. So when I measure my peak voltage, which you won't really measure on your meter because your meter is calibrated for RMS, but you're going to get a lot more power once it's been rectified. But that's what they mean, line to line and line to neutral. 220 volts, line to neutral, 400 volts, line to line. And it works the opposite for power. So your line to line current will be less, but your line to line voltage will be more. Your line to neutral voltage will be lower, but your line to neutral current is going to be much higher. I know it sounds all complicated, but that is the way it is. And those are the joys and advantages of three-phase. So you guys might come across a circuit like this in an inverter drive when you open it up. So three-phase diode front-end circuits like the one shown above draw current in pulses. For a 6-pulse drive, which is the most common in use, we can see 6 pulses of current in every AC cycle. Each pulse of current occurs when the AC supply voltage is greater than the DC bus or capacitor voltage. And remember, I said to you, capacitors draw non-linear power. So just to refresh what I'm saying, and it gets a little bit important now, these diodes are only going to conduct or pass power through them depending on how much this capacitor is drained. So if this capacitor was charged, and these caps will stay charged at about 520 volts, that's why we have big signs on them, do not come near these. They are enough to take bits of metal out of your screwdrivers when you discharge them because the energy they hold are very dangerous. So you must know what you're doing if you want to try and measure this power. But these will stand 520 up to 560 volts. If this is the motor, now my inverter compressor will start to turn. It takes its power not from the electricity, it takes its power from these capacitors. So if this capacitor only supplies it, say, 30 volts to start running, then this capacitor is only going to take 30 volts of my waveform coming in. And that's going to be a problem. And because it only draws in a discontinuous manner, and when it needs power, this is what it starts doing in reality to my waveform. This is very, very sort of bad on my supply voltage, and my bus, my DC, my AC bus, my red, yellow, blue. This is what's happening. You can't see it, but this is what's happening at electrical levels, which is very unhealthy for the system. And this starts generating harmonics. So the waveforms here, it's a big fancy word, but are what we call a superposition of the input red, yellow, and blue wire currents into the drive. So if I had 3 current sensors, imagine I had a current sensor there, those round toroids, 1, 2, 3, and I scoped the waveform. This is what the waveform is going to give me on an oscilloscope as these diodes conduct in pieces to charge this capacitor. This is what they're doing to my waveform. And that big fancy word of superposition is pretty much if you have, let's say you're at a beach and you have 3 or 4 different waves coming through at different heights and different angles. If you take, say, 3 waves washing up on the beach, you add each of their heights up. The one may have been 2 foot, 2.5 foot, and 3 foot. You add them up and you do the common mathematics, and you can create a superposition of all 3 waves in one wave. That's what the word superposition. You take all these waves, add them together mathematically, and you'll have the ultimate waveform, what you're seeing over here. So when the supply voltage is balanced, now I'm not talking current here, guys, I'm talking voltage, pressure. Voltage is the pressure that pushes the electromagnetic field, and the moving electromagnetic field is what we call current. Okay, so when the supply voltage is balanced, each diode conducts the same amount of current for the same duration. Remember I said voltage is pressure. So if I'm pushing equally at 400 volts on each wire, I'm therefore going to push the same amount of electromagnetic field through the wire, or current. If I'm pushing with 400 volts on the one wire, 380 volts on the other, and 390 on the other wire, I'm going to have different amounts of current flowing through the load. The load's not going to be very happy. I need to have balanced pushing pressure or voltage. So the area under the current waveform essentially represents the power required to operate the load. So I haven't colored this in yet, but all these little black areas under the wave, that is the power that my load is drawing. Any line inductance, now also an inductance is whenever you have a coil in a wire, so pretty much whenever you have a motor. Okay, so any line induction will also cause what we call a commutation overlap, as shown below, where the green current assumes the current from the blue supply. And that's more for the technical guys that have a bit of electrical background. You can see the commutation overlap and where this current assumes. They're not nicely in electrical degrees. The green is starting to pinch space because of mutual inductance. So I'm showing you this graph again. Capacitors do not pull current smoothly from the line like a typical linear load. And I remember that line I showed you earlier on. It would come up and it would be a nice smooth line. But as the capacitor's waiting to do work, as the capacitor starts doing work, starts what's happening. It drains and it suddenly charges. It'll drain and suddenly charge on the different phases. And now as it drains down here, and suddenly the load doesn't require any more power, and the electricity supply quickly recharges the capacitor. And this is what we call a line notch. This V, this valley, and this notching is what leads to harmonics. So how do we sort this out? This is very bad news for a supplier. So to try and smooth out the notches in the line, extra diodes are added to the bridges. As a standard 3-phase VFD, we'll use 6 diodes, as we've seen in the training. So we're going to have 6 diodes, 3 phases, positive and negative. 1 diode for the positive, 1 for the negative. There's 2 voltages. 3 times 2 is 6. Okay, so we need that to rectify AC to DC. Therefore, we refer to it as a 6 pulse, as I've told you. And now, as you increase the number of rectifier diodes, sorry, I'm just moving, my mouse has just moved there. So as you increase the number of rectifier diodes in multiples of 6, you're adding now more pulses to the DC bus, okay? And therefore smoothing out more notches. Sorry? So you have to, sorry, I just had a bit of interference here. So you may have now heard of a 12, 18, 24, and 36 pulse drives. So in order for this to work properly, we have what we call phase shifting transformers. I know this is getting quite technical, but some sites have so much inverter technology plugged in on them. They have to have up to 36 diodes built in just to rectify the voltage, okay? and a phase shifting transformer. So this is going to add significant cost and sizing to electrical cabinets. So I've just shown you, I'm going to show you here pretty much an 18 pulse rectifier. So this would be a very expensive inverter, maybe to run a pump like a Danfoss inverter. So this design now draws power 18 times, which is 6 times per phase for each of the 3 phases per each complete sine wave circle. So here you can see this would be there's my load. Let's say this is a pump that I want to run. You will see I have 18 diodes plugged in. There's my huge bank of capacitors that are going to supply the power. All these diodes are going to be doing is purely charging up this bank of capacitors. But because I'm delivering so much power, this might be a massive motor. It needs a lot of power, so I need a lot of capacitors. Let's say I'm going to exaggerate, 10 capacitors here. I can't have 10 capacitors drawing off 6 diodes, but if I have 10 capacitors drawing off 18 diodes, I'm going to have a lot less ripple. And as you can see here, this would be a slightly different design on my transformer. This is a delta transformer. You'll see there's no neutral here. Okay, there's no neutral on the delta. It will go through the windings. And then here we're going to star the network. So this will be my sort of in phase, and here I'm going to phase shift a few degrees, and you'll see there we're phasing up and here we're phasing down. So this is my supply transformer, and here we're pretty much shifting the phases, because you can't have 18 pulses coming and you're going to blow it up. So we need to retard or slow down the speed of the electromagnetic energy coming into the transformer. So I know this sounds difficult, but what's the advantage of this? And it is difficult and confusing. There's no jokes about it. But I'm trying to show you how to mitigate bad harmonics on a system that requires huge power. So this rectifier will eliminate this notch voltage input and produce a much more acceptable input current waveform with all notching removed. And that's pretty much the waveform we're going to get. If I only use 6 diodes, that's what's going to happen on my transformer. But if I use 18 diodes, we smooth out all that notching, because we're charging all the caps with 18 diodes now instead of 6. So there's less notching. So that is why we have 18 or even up to 24 volt bridge rectifiers. But the problem with these, they're fantastic, but they're very expensive. The engineering involved, phase shifting transformers and having these bridges. But if you've got to get it done and you're having a lot of this on your site and you need this, then it's pay up and look big and go for multi-pulse rectifiers. So let's quickly go back now to our conventional 6-pulse rectifier. After we've been confused by that, let's keep it a bit simpler and we'll stick to the 6-pulse. So when the supply voltage, remember voltage is pressure, the pushing power. So when the supply voltage is balanced now, each diode is going to conduct the same amount of current for the same duration or time. So now the area under the current waveform essentially represents the power required to operate the load. So now this is what's going to happen inside the bridge on a balanced supply. Now remember, you'll remember these notches. We don't have money on site, so we've got this standard 6-pulse rectifier. And this is as the capacitor is drawing power from the bridge. Rectifier, you're going to see the bridge. This is the power I've highlighted in the sea blue color. This is the power I need to overcome the inertia of my motor. I need to rotate my compressor. So as I said, this is what's happening inside the bridge on a balanced supply. Remember, balanced meaning the voltages are at equal pressure, guys. This notch I'm not going to get rid of, because this is as my capacitor discharges and recharges my load. And there won't be one capacitor here. There'll be up to 5 or 6 capacitors doing this work. Else you need a capacitor the size of a dining room plate. It's huge, it's impractical. So we add multiple power capacitors on big loads. So let's have a look here. Now, as the voltage unbalance or imbalance increases. Now we're not at 400 volts. I might suddenly, two phases might be running at 400 volts. Now suddenly I have too many single phase loads switching on, like microwaves, ovens running, people switch kettles on in the office, in the factory. And now suddenly the pushing pressure, let's say on my red phase, drops from 480 volts down to maybe 380 volts. This is pretty much what I'm trying to tell you. So as the voltage imbalance increases, one or more of the diodes in my bridge are going to stop conducting. Now this is where the course sort of gets a bit interesting, because I'm teaching you the dangers of voltage drop. Okay, so now what happens is one or more of the diodes is going to stop conducting, and the current draw will look now starting to look like a large single, look like a single large pulse, similar to what's been seen on our single phase power rectifiers. That's a single phase I showed you at the beginning of the training. The large pulse of current is now going to be shared with fewer diodes. Remember, we've only got 6 diodes. So now the ones that aren't conducting, the other 4 diodes are going to have to pick up the workload. And what happens when they pick up the workload? They're going to thermally overstress the diodes by heat. They're going to get too hot. Since the power delivered to the load is a constant value, the area under the curve waveform has to remain the same. So if I have a motor that's spinning in, it needs 500 watts or 1000 watts. The motor doesn't care what the bridge is doing. The motor doesn't care how many people have put kettles on or switch lights on or running microwaves. The motor doesn't care. The motor has a job to do. The motor's drawing power, say 2000 watts an hour, and it needs that power regardless. So what happens is the power remains constant, and therefore the blue area remains constant under the graph. So if I start getting a voltage drop, say from 400 volts down to 380 volts on my one wire, this is what's going to happen. You will see that, say, the yellow wire is the phase where there's too many single phase loads in the building. Everybody's boiling a kettle, it's lunchtime. Everybody's making toast, it's lunchtime. Everybody's running a microwave, it's lunchtime. So the 400 volt pressure starts to drop on the yellow phase in the building. But my load is still needing the same amount of blue power. But now you see, because the yellow phase has dropped, my motor is still pulling 2000 watts. So it starts pulling more work through the other 4 diodes, which are supplied on the red and the blue phase. So you'll see they're having to work a lot harder now. They were working at that height, but now they're suddenly supplying huge amounts of power. And here we go back to our drawing, and we will see that those 2 diodes are not working anymore. They're hardly doing work, which means these other 4 diodes picking up the work. So additionally, supply voltage imbalance will also cause now, remember, supply voltage, we're not talking current, we're talking voltage, pressure. Okay, so pressure imbalance will also cause the DC ripple in the capacitors to increase, thereby creating additional heat loss and decreased service life of the capacitors. Ripple current degrades a capacitor by raising its internal temperature and affecting the electrolyte conductivity between the aluminium foil. This raise in temperature then affects what we call the leakage currents of these electrolytic capacitors, as well as the aluminium's resistance. Power loss in electrolytic capacitors. Now remember, power, my caps supply the power to my compressor, to my motor, but now I'm losing power in them, so they're not going to work anymore, but my load still wants power. Okay, so power loss now in the capacitors is mainly due to voltage changes across the dielectric. Depending on the settings, the drive may also trip on overcurrent. So if you remember the beginning of the training, this is the typical wave train on a balanced voltage system, nice and smooth and linear. And you'll see if I measure the height difference between here and here, so this is the cap when it reaches its lowest voltage, and this is its maximum voltage as it's applying the load. My ripple, my alternating current ripple pulse, it's very small. So this wave train now looks different because it's downstream of the bridge rectifier compared to what I showed you here. This is what you're seeing here is what the capacitor is taking from the bridge. And this is pretty much what you're seeing as it's supplying the load. So just to refresh, each time a pair of diodes conducts, it draws a large pulse of current, as discussed in the previous slide. This is essentially connecting a capacitor to the supply, wherein a large pulse of current with a magnitude of which will depend on how pretty much how charged and discharged the cap is. Also on three-phase, if the one phase has a slightly higher impedance or resistance compared to the other phase, then that is usually reflected in the current pulse. So you might have impedance is what when we talk alternating current, we talk impedance. When we talk direct current, we use the word resistance. Two different terminologies. For the simple reason, for resistance in DC doesn't involve magnetism. There's no magnets involved. Yet in AC, we use electromagnetism, and we use the word impedance and reactance in the cables. Okay. So impedance is also the resistance of the coil. So I'll put your note in the figure below. One phase has a 1 ohm resistance, while the other two have 0.1 ohm. So this is very subtle, but very serious. 1 ohm doesn't sound like a lot if you measure a piece of cable. Let's say you take a piece of cable 3 meters long and you measure red to red wire on your meter. You put it on ohms and you see, you're getting 0.1 ohm. You measure blue to blue, 0.1 ohm. You measure yellow to yellow. Now suddenly you're getting 1 ohm. That's a big problem. You can't use that piece of cable. They all have to have the same impedance. So how would you get 1 ohm? Well, possibly the cable's been dented, damaged, the insulation cut, and you're getting some leakage power. And 1 ohm doesn't sound a lot, but when you're talking power electronics, it's huge. And here I've put you can see the difference in magnitude of current draw for each pulse just because of a little piece of damaged cable. And 1 ohm is nothing, but it's a lot more. It's 9 times more than 0.1 ohm. And now you can see from a power point of view how my power is going to fluctuate and the problems it's going to cause. Why? Because look how much more massive my peak-to-peak ripple current's got. So I'm feeding this ripple current now into my capacitors, and they don't like this up-down bouncy, and they start getting very hot. What happens when they take a lot of ripple current? This electrolyte, which is like a bit of a paste or a bit of a liquid, it starts to degrade, it starts to boil, it starts to overheat. And this is the dielectric I was talking about, and these little zigzaggy things is the aluminium foil, and that's what a capacitor is. It stores electric field charges on this aluminium. It's the same aluminium like you get in your kitchen, okay? Exactly the same aluminium foil, but energy is stored in an electric field on these aluminium foils. These aluminium foils are not allowed to touch. If they touch, there's an explosion. So you have a dielectric, which sort of prevents them conducting or touching, and you have your electrolyte, which sort of creates a magnetic field. But this electrolyte starts to boil. And when it boils through too much ripple, the capacitor isn't happy, and it starts to become like a steam bomb, okay? And I'm sure you guys have seen this on some PC boards you've opened. This is what too much ripple voltage does to your power electronics. All these capacitors, because of maybe a supply cable that is damaged or a 15-volt difference between phases, will start boiling these capacitors. And you will see here, that is why capacitors are cut with X's. These are pressure relief valves. When that electrolyte starts to boil and they explode, like this cap exploded, it doesn't explode sort of sideways, it blows to the top, like a little rocket ship, and it blows the cap upwards. But these pressure relief valves open to release steam because those aluminium foil has got so hot it starts boiling steam, all because of low voltage, okay, and or a impedance issue on one of the supply cables. So below is an example of our typical variable frequency drive charges the capacitor. So this gets a little bit technical, but it's interesting. So because capacitors supply power to the load, remember it's all along the load, the motor, the compressor, that is the load. So capacitors supply that power to the load. Okay, variable frequency drives now typically have a very good overall power factor of around 0.96. You guys may have heard of the word power factor. Power factor is pretty much how efficiently you use power. And power factor also has to do with the magnetizing power required by the stators to get the motor rotational. So because the capacitors are supplying power, they're supplying power to the magnetic fields as well as the real power. So therefore we have a very good power factor of about 0.96. But let's have a look at a circuit. This is typically a circuit you'd see in, let's say, a VRV design, a three-phase VRV. And you look at this and you go, whoa, this really looks complicated. But if we deconstruct it and looking at the training we've done, this is the front end. There's my supply capacitor. Sorry, that's my shunt capacitor. These are more capacitors, all there to store power. These are sort of just shunt resistors to stop the caps overcharging per se, and they supply power to my IGBT module, switches these thyristors on and off. This is all single phase, by the way, DC, I should say, direct current, goes through 6 RGBT. This is RGBT module or silicone controlled rectifiers, and you'll see these little push things on you. We put a voltage on that and acts like a little spring, and it pushes and it conducts. And here's our inverter driven compressor. So we take DC out of the capacitors and we recreate 3-phase. But that's another training course I do. But this is just to show you the basic principle. But we're not really worried about what happens down here. We focus primarily on here for this training session. So what happens? You'll notice if you look at this diagram, you'll see, hey, hold on, only that line is solid. These lines are open, which means open circuit. Yet the middle phase it's hot, it's live. So what does that mean? Let's have a look. So, okay, the voltage can't flow through there, but it goes down through here and it waits. It's sort of a relay. But interestingly as well, okay, so that stops at the relay, it's doing nothing. But if we look previously here, we'll see that this was always a constant line. Okay, so we're learning a few things. We see, okay, that goes through the one diode. Okay, so what's actually happening here? What's pretty much happening is we pre-charge these capacitors. The caps now get pre-charged to 320 volts to avoid electromechanical stressing of the components. And these caps also draw massive current. So when they're discharged, they're just sitting there. But when they initially charge, those aluminium tin foil inside draws massive power. And that's why you have that huge current spike as these initially charge. But I said to you early on in the training, these can easily stay at 560 volts. But we can't charge them up to 560 volts straight away. We need to warm them up. It's like you don't just take your car to a red line in the morning. You start it up gently and you get the engine warmed up. Here we're warming up the capacitors. But notice now that this is a green line. It goes through this diode. It charges the capacitors. Now it suddenly changes to a blue line. Now you'll notice on capacitors, they have a plus and a minus sign on them, okay? Electrolytics do. Therefore, you have to put your meter on DC to see what voltage is on here. But what's happening? Why is this changing from a green line to a blue line? Well, pretty much here's the little secret. We've taken a neutral wire, comes here, and it waits at this relay. But we also see that the power comes in and it waits at this relay too. So what pretty much happens, you get the motherboard. The motherboard will send a little 12-volt signal for this relay to close. When this relay closes, it takes 220 volts to shut that relay. And what we're doing is we're feeding the neutral. So the AC done work through the load, and now it can return to the transformer through the neutral. Remember, I'm only using single phase here. I'm borrowing one of the phases from the free three-phase to control the coil in this relay. And this coil is purely there to provide a return path of the neutral. Remember, we're talking, if you had to measure this, you would not get 220 volts on AC. If you measure this, sorry, you get 220 volts AC, but you're getting 320 volts DC because these caps charge on the peak. So it's quite an interesting scenario. Now the motherboard sits and it waits. It's done its job. So now once the caps have been charged on the single phase line, a voltage monitor sends a signal now to deactivate the charging relay. Here's the charging relay. So a voltage monitor has sensed that these caps are sitting at 320 volts. So now bang, that goes off. And I don't need the neutral anymore. Now this other relay comes in. This will be on what you call the noise filter board, and this relay will cause that contact to shut. Remember, so now further signal will be sent to this relay, 12 volts, to energize and latch the other two phases. And now this would then charge the caps on the peak value. Now, once these are 320, they're going to now rocket up to 560 volts. And I don't need the single phase circuit anymore. So this isn't really bespoke or a unique design to Daikin. It's a sort of economical design that works very well. But there's problems that come in when you lose voltage. So this is an ideal world, a happy day where we're getting 400 volts consistently, brand new bowl, and everything's happy. 6 months down the line now, we're going to suddenly start blowing boards. And we're going to blame load shedding, we're going to blame lightning strikes, or we're going to just say the manufacturer makes rubbish boards, which isn't actually the case. All three of those scenarios are incorrect. And to describe what I've pretty much drawn here, this is sort of what you can visualize. It's always nice to see a more picturesque thing. These are the capacitors that supply work. They supply the not the transformer, they all supply the compressor or the motor to turn the pump. Here's a little bridge rectifier I showed you earlier on. Here's a switch mode power supply. You see all these caps, they're supplying up to about 8 or 9 different voltages. So I said to you earlier on in the training, if you look at just this little section, this is my switch mode power supply built in on my power electronics. Here's my big bridge rectifier, which is bolted to an aluminium heatsink. Underneath here, there's a big block of aluminium to help cool these down. As they short circuit, they'll short circuit as these are recharging and discharging. These cause these to short circuit, and as they short circuit, they get very hot. We need to dissipate them, that heat, into a big block of aluminium. But if we have a look here, we see this little tall boy here. This is what you call a shunt resistor, and this little relay. My motherboard will use my one phase, my L1 will feed this relay to shut it. It'll provide my neutral return. So once these caps are charged, it'll go out my neutral wire. This will actually be my neutral plug here. Okay, it won't be on those 3 phases. And this shunt resistor is there to absorb any inrush current or spark to stop damage to primarily this relay. It will allow, so single phase will charge these relays, and this relay, these capacitors, and this relay will then shut and provide a return pass for the single phase. Once these are sitting at 320 volts, that little computer chip there will say, I'm happy. Open that relay. That neutral circuit becomes useless to man or beast. It will then send a signal to this relay, and this relay is dealing with a lot more power. Here it's dealing with 2 phases. It's got a much bigger shunt resistor. That phase is already hardwired to the caps. It's going to bring in this phase and this phase through this relay shunt resistor, and these caps are going to be ready for work, sitting there at 560 volts. So that's pretty much how these boards charge up. But the problem now comes in when we start losing voltage. So I'll put here, what problem would undervoltage suddenly cause? As I said, let's imagine lunchtime. Kettles are going, toasters are going, microwave ovens are going, and everything is being poorly designed, and it's only, say, plugged in on this phase, and this phase suddenly drops to, say, 380 volts. These capacitors are supplying very large amounts of power to the IGBT module, which is here, which is supplying the load. If the voltage drops below 320 volts, say to 300 volts, then the single phase circuit now cannot re-energize to pre-charge these caps while they are busy supplying power to a thirsty load. The capacitors are now going to continue to draw maximum voltage and current from the bridge rectifier in order to want to supply what the load is wanting. So let me break that down in simple English. The load is doing work. It's using 2000 watts of power in 1 hour. This is what is supplying the load. No, it's commutating the load. It's taking its power from here. This is supplying these switches. These switches are diverting the power to the load. Now, as said to you all along, if these capacitors suddenly drop below 320 volts, down to 300 volts, we cannot re-energize this circuit. It can't, everything is happening so fast. These caps need to run at least 320 volts. When they drop to 300 volts, because I'm not getting enough pressure to charge them, because this phase is being drawn because of a bad design on too much single phase, I cannot quickly re-engage this circuit to charge the caps, because that means I have to open this relay. If I open this relay too quickly, there's going to be a lot of flashing and arcing, and the relay is going to burn. Then I have to quickly charge these up, disconnect this neutral circuit, relatch this relay. It's too much happening, too much arcing, sparking. So the initial circuit designer now has selected a bridge rectifier to deal with a maximum current carrying rating, namely how much heat it can handle. So in this type of operation condition, the bridge will fail due to overheating. So the guy that's designed this fancy circuit says, listen, these diodes can only get up to about 90 degrees or 80 degrees. When this phase drops, these 2 diodes here will get up to about 100, 110 degrees. And when they get to that temperature, bang, they explode. And my whole board detonates. Because the voltage is dropped, I can't recharge these caps. These caps now are taking too much power out of the remaining 4 diodes. These 4 diodes now were operating at 80 degrees. Now they suddenly go up to 130 degrees. Within about 30 seconds, bang, this whole bridge blows up. All because too many people are boiling kettles, running microwaves, and making toast on this phase. Okay. And this is technically another fancy design. A lot of manufacturers are using these. These are about 1,400 Rand each, this little thing. What this does, it has all these 6 thyristors built into it, as well as these 6 diodes. And that is how we miniaturize power electronics. So when that blows, bang, you're going to blow everything, and your whole inverter board goes. Not because of over voltage, not because of a gecko running over a board, purely because either an impedance is incorrect. This line might be measuring 1 ohm instead of 0.1 ohm, or at lunchtime, too many people are plugging in single phase. Your whole inverter board is going to blow because the voltage has dropped too much, because this load is very thirsty and it wants constant power. So voltage imbalance or voltage pressure isn't a power quality issue in the sense of the quality of the sinusoidal waveform of the electrical supply or events occurring on it, like harmonics or transients, for example. It is nevertheless of critical importance for a variety of other reasons, which I'll quickly get on to explaining. So this graph might look all confusing. It is for the non-electrical guy, but you can remember this whole training I've shown you guys this fancy little pattern. And here I'm introducing another thing called degrees. These phases are separated by 100 degrees, peaking at 325 volts. For example, this would be, say, single phase, normal 230. Imagine this as a single phase coming in. My nominal voltage would be 220. This is peaking at 325, my peak. But if I deconstruct all these fancy little squiggles, I'll make it far easier. This is a lot more easier for you guys to picture. And here we'll see a nice balanced voltage system. If I take a ruler and I measure there to there, it would be, say, 2 centimeters. Hey, that's 2 centimeters. Yep. And that's 2 centimeters. Those 2 centimeters, let's rather translate, would mean 325 volts. So we'll see, hey, that's 325. Hey, it's a nice happy system. So we know the pressure is nice and correct. We'll also know if I take a protractor and I put my protractor here, there's 0 degrees, and I measure there to there, hey, like 120 degrees, here to here, 240, 240, 360. Wow, this is spinning perfectly. It's nice and balanced. My pressure is nice and equal. The lines are the same length. And also the spacing between the lines, the vectors, is nice and evenly spaced. Now suddenly we start getting under voltage. So an unbalanced three-phase system now will suddenly have voltages. They're not all equal in magnitude, meaning height or pressure, and or each of the three phases are not 120 degrees apart. So when we start getting a difference in degrees, sorry, I just hit a banging door there. When we start having our degrees suddenly start going out, that has to do with magnetic fields. I'm not going to confuse you guys too much with that, but let's rather just see a picture. Now suddenly things start going haywire in the building. We're like, what the heck's going on here? We've got a voltage monitoring system on, and things start going crazy. We're like, whoa, whoa, whoa. So here pretty much we see two phases start dropping. I'm going to use my old lunchtime analogy thing. Maybe the 3rd floor and the 7th floor are on different phases in a building. Everybody's going to lunchtime, boiling kettles. Suddenly these phases drop in the building. Now my VRV system is still requiring a lot of heat cooling. People are boiling, they're making toast, they're eating, their metabolism's going up. Now the VRV system needs to make more cooling to cool the building down. So it starts taking more power. At the same time, other people might be running rotational equipment in the building. There might be a guy using a drill. Somebody's using a hairdryer. They've had a shower at lunchtime, and these create magnetic fields. So suddenly, my voltage and my current go out of phase. They're not running in line, so my degrees start messing out. Whoa, and now we suddenly see. This is a lot easier to understand than all this fancy stuff, but this is a vectorial explanation. Now we see, whoa, C and B are pulling a lot more current. A says had a voltage drop, and if I put a protractor here, I see there's about a 5-degree angle. Whoa, everything's going out of phase now. Okay, bang, bang, jeepers, and this is starting to mess with my whole supply system. Now bear in mind, this is what's happening on my supply. My VRV system, for example, is drawing off of the supply, and I start feeding this unbalanced information and power into my capacitors, which ultimately has a huge effect on my voltage imbalance, which, as you've seen, creates PC boards to blow up. Not over voltage, under voltage is what's causing boards to blow up. Too many devices are being used in the building at once on single phase. Even too much fluorescent lights suddenly get switched on. There might be 150 lights that suddenly switch on. They create a huge voltage drop and a lot of harmonics in the line. So we're almost done with the training, but I'm just going to show you a balanced three-phase system has what we call an anti-clockwise rotation of the electromagnetic field. And when something rotates anti-clockwise, it's what we call a positive sequence. Okay. So I'll show you a little picture now to help you understand this a bit better, but a current or voltage imbalance between phases in magnitude. So magnitude means 400 volts to 300 volts. Sorry, 400 volts is say 380 volts, or a phase angle. So phase angle would be affected by magnetism. Anything that turns, be it a drill, be it a hairdryer, be it a pump, be it a vacuum cleaner, everything that has a motor is suddenly going to affect the phase angle in the building because of the magnetic fields that need to be established. So the moment I have a voltage imbalance due to a voltage drop or magnetic field switching on, it's going to give rise to what we call negative or zero sequence components. So, whoa, what does all of that mean? Well, let's have a look. This is our ideal building. Say, new build, you're on commissioning day, not everyone else has been in the building, and you commissioning, everything's working well. You're going to have a positive sequence in the building, and it's going to rotate. The electromagnetic field is going to rotate anti-clockwise. Now suddenly we have voltage imbalance because toasters are getting switched on. Guys, 3 of the floors of the building are all using vacuum cleaners at once. Guys are running, if the building's got a canteen, guys are frying chips, burger machines are going. It's all going to create a drop in pressure. So now I'm going to create a electromagnetic field that's going to want to turn this way. And we're going to have also what we call a non-rotation field, but an added vector components. You generally get that. I'll show you on the next page with harmonics cause that. So if I add on what's happening in my building up this, I suddenly get my original system looking very confused and a huge current or voltage draw on my one phase. So this primarily has to do with problems with rotational machinery. So yeah, I'll quickly, second to last page. So I'm going to quickly show you the problem now. We've been primarily speaking about what happens to PC boards and how they blow up. We're going to move away from that now, and we're going to primarily look at what voltage imbalance and phase imbalance does to motors. Why do your motors cook in a building? Why does a pump motor suddenly burn out? Well, let's have a look. A voltage imbalance or voltage pressure difference is caused by single phase loads drawing a current on the phase they're connected to, which won't happen on the other 2 phases. The uneven distribution of general single phase loads across a 3-phase system can also sometimes be bad enough to create a voltage imbalance. This more often than not occurs over time as an installation which was initially balanced during its construction and commissioning has additional circuits or equipment added to it. So every time you even photostat and use your photostat machines draw huge power because of the corona they need to heat up. You get these spikes. So here we look here. Let's imagine this is a motor supplying a chiller with constant chilled water in a building. If I have more than 1% imbalance, I'm going to derate the motor by 98% of its workload. So if it's spinning an impeller and I need to supply 10 liters a second through my chiller, I'm now going to start supplying 8 liters with the risk of my evaporator starting to freeze. Okay? Or my flow rate, I'm going to have a lot of alarms on site because of the flow switch that's fluttering. But a 5%, which is still sort of within acceptance of SABS standards, and it hasn't to do, the SABS put these standards in place primarily to stop cables burning and catching alight. They don't really care, in inverted commas, what it does to the performance of your building. but within the SABS tolerance guidelines, I lose 75% performance of my motor. So now I could go down to, I don't know, 6 liters a second instead of 10. The chiller keeps on tripping. Get the guy out there to look at the chiller. They can find nothing wrong. In the afternoon, the problem goes because the single phase loads get switched off and everything's back to normal. So this is just the effects it can have on, say, a chiller with anything that rotates. A non-inverter chiller, by the way, standard compressors, or a chiller operating a pump, primarily the motor supplying the pump. So I'm going to have a huge water flow issue. So according to the IEC, which is the sort of the head honchos that put compliance together and as acceptable standards. So according to the IEC, voltage unbalance is defined as the ratio of negative sequence voltage to positive sequence voltage. Remember, positive sequence and negative sequence has got to do with the rotation. Positive sequence spins anti-clockwise, negative sequence clockwise. So what does that all mean? Briefly explain, these three-phase voltages can be then mathematically expressed as a sum of positive, negative, and zero voltage sequences. So harmonics also cause a problem, such as the seventh, which rotate with the same frequency. So I'll break this down for you. If you have too much harmonics, say the first harmonic is what Eskom supplies. Then you get the 7th, the 13th, and 19th. What these do is they rotate in the same direction. Sorry, I'm jumping the gun. So these harmonics will rotate with the fundamental frequency in the same direction. Okay, in an anti-clockwise direction. If I look at zero sequence harmonics, these guys pretty much do nothing. The third harmonic we get a lot in star transformers. That's why the neutral is there. The neutral takes away, carries the third harmonic back to the transformer and tries to sort of get rid of it. But these also don't rotate at all because they're in phase with each other, called zero sequence. So all these are going to do, if you have harmonics and a guy says, hey, your harmonics, your machine's causing harmonics, most times they don't really know what they're saying. It's an incorrect statement from them. But let's say the guy says, hey, the 9th harmonic is causing problems on our system. All it's going to do is cause your neutral wire to get hotter. Why? Because it's running also in phase with the fundamental, and the fundamental is going to cause my motor to spin this way, anti-clockwise direction. The problem comes in with your negative sequence harmonics. So harmonics such as the 5th rotates in the opposite sequence as the fundamental, and these are called negative sequence because now they're going to turn clockwise. So you have a motor that's spinning with nice torque going this way, say, I don't know, 500 Newton meters of torque. Now, because of voltage drop and my diodes on my bridge rectifier somewhere down the stream, they are creating now negative harmonics, and they're going to create a magnetic field wanting to spin this way. So what's that going to do? It's going to affect the torque. The torque is the twisting power of my motor shaft. So now my motor is going to go, it's going to not deliver the power I need to perform work. And this is how crazy yet important harmonics is, and harmonics are generated by diodes, which I showed you in the beginning. So diodes in switch mode power supplies create harmonics. Harmonics feed back onto the supply, and they affect the magnetic fields and the way magnetic fields turn motors. And we've also learned from the course how influential low voltages and how damaging it can be to PC boards. So low voltage causes a lot of damage to PC boards, and a lot of harmonics due to a lot of switch mode power supplies and a lot of units with diodes cause magnetic fields to spin this way or that way, and they affect motor torque and power delivery. So in concluding, here are some facts that attribute to voltage imbalance. The supply voltage, first of all, from Eskom would be unbalanced. Or, and often overlooked by the way, unequal impedances of three-phase distribution systems. Unbalanced loading on power factor correction like capacitors. I didn't really get onto power factor, that's another training I do, but you can just put this in your memory bank. Unequal distribution, the main Achilles heel of single-phase loads. Unbalanced loads, even if connected in three-phase. So possible single-phase induction motor, okay, can also cause this. And mismatched transformer taps. Not always the case here. Primarily single-phase. Power factor issues are your main problems. Let's say owner operated faults. This isn't owner operated supply voltage, and also some poor installation work can create damaged cables or unequal length cables. So for example, if you have 3 motors running in a coming off the same panel in a plant room, and all 3 motors are running at once, you should have all 3 motor cables the same length. So if the furthest motor is 5 meters away from the DB, cut the cable 5 meters here and 5 meters here as well, because this motor is going to draw a lot more. This motor is going to have, say, the 0.1 impedance on the cable, whereas this motor here will have 1 ohm impedance, and you saw the effects it can have on harmonics and under voltage supply to other loads. And it pretty much just gives you also a nice balanced load, having the same cables, if they're all coming off in the same plant room within the same vicinity. So here are some of the effects and problems caused by voltage imbalance, which we've seen. So increased heating and reduced life of induction motors. And that's the positive and negative rotation that I shared with you. Reduced life of variable frequency drive front-end diodes, which you've been through. I've shown you how diode bridges, rectifiers explode, and or bus capacitors. You've seen these caps get hot, they boil, and they explode. And depending on the type of load, reduced voltage can lead to an increased current in one or more phases, hence increasing losses. Okay, thanks for your attention. I don't know if anybody has perhaps any questions to ask. Or did I lose all of you after about 7 minutes?